Hello everyone. Today we're going to talk about vectors, and in this first video we're going to look at decomposing vectors. Now when I say decomposing, you may think of honestly roadkill, a dead body or something like that. What's happening with decomposing is that is breaking down to its more basic components. When we decompose vectors, it's the same exact principle. We're breaking a single vector into its horizontal and vertical components. So let's look at the handout for vectors, and this one with decomposing resultant vectors is called. We'll look at number one. It says, consider a baseball hit at an angle of 32 degrees from the horizontal with a velocity of 123 feet per second. How much of this vector contributes to the baseball traveling upward, which would be your vertical direction, and how much of this vector contributes to the baseball traveling horizontally, that being your x direction? So I just did a quick sketch. Your overall resultant vector, or your end result of the whole motion, is this 123 feet per second vector at 32 degrees from the horizontal. Now, when we decompose it, we're simply breaking it down into its x and y components. And remember, to get the x from, if you think back to converting between polar and rectangular coordinates, x is r times the cosine of theta, y is r times the sine of theta. Very simply put, r being the magnitude of our vector, or in this case it would be 123 feet per second, and theta being the angle, which in this case is 32 degrees. So to get the horizontal component, you just take 123 times the cosine of 32 degrees, you get 104.31 feet per second. The vertical component is 123 times the sine of 32 degrees, which gives us 65.18 feet per second. And what that means is after 1 second, strictly horizontally speaking, it's traveled 104.31 feet, and strictly vertically is traveled 65.18 feet. But it's not going in step fashion like that. It's going in a diagonal, which is really the end result of the baseball itself. Now that's pretty straightforward, and most of them will be pretty straightforward. Anytime you have to decompose a vector, that's all you're doing, finding the x and y components. But if we look at number 3, I'll let you try number 2 for practice, and the answers are there. But if you flip to the second page and look at number 3. It says, consider a 3,500-pound car parked on a driveway that has an inclination of 5 degrees. Ignoring friction, what is the minimum brake force needed to keep the car from rolling down the driveway? Now, here we have the situation where we have the 5-degree incline, car sitting on the driveway. Now, normally, our xy axis, our x-axis is horizontal, our y-axis is strictly vertical. Now we're on a 5-degree tilt, which means everything tilts 5 degrees. So our actual xy axes are here, and the weight of the car is the actual vector. The weight is a vertical vector downward, because weight's always directed downwards towards the center of the earth. So our angle in standard position, we come around to our vector here, which normally, like upright right now, my weight would have an angle of 270 degrees. We always start at the positive x-axis, so we go around to our weight vector, which is strictly downward. But since that's tilted, it's actually 5 degrees shy of that. This is 5 degrees here, which means our actual angle that we're using is 5 degrees shy of that 270, or 265 degrees. So if you want to go ahead and decompose into both your x and y, that's fine. To get the horizontal component, remember, it's r cosine of theta. To get the vertical component, it's r times the sine of theta. So you take 3,500 times the cosine of 265, you'll end up with negative 305.05 pounds. The negative is denoting direction, technically to the left in this example. If we're doing the vertical component, 3,500 times the sine of 265, that's a negative 3,486.68 pounds. Again, that's negative because it's downward, and vertically speaking, down is negative, up is positive. Now, to answer the actual question, what's the minimum braking force needed? If you're on a level surface, it's not going to move left or right, horizontally speaking. So that would be 0. But with a slight inclination, our actual answer is that negative 305.05 pounds. If you look at each of the two answers, we're trying to stop it from going horizontally. So we would want the horizontal component. Now, if it's falling in free fall, vertically speaking, we'd have to have a force equal to the weight of the car itself, which is 3,500 pounds, to stop it from moving vertically. In other words, as a car sits at rest on a surface, the ground is actually pushing up with 3,500 pounds, or else the car would be falling downward. Right? But in general, and we'll talk about more of that in physics, in general, we're just decomposing the vectors and finding one component. In the next video, we're going to look at actually finding the resultant vector, which is the opposite of this, given several individual vectors all working together.